a form of energy which is called the thermal energy, and it could be defined as the transfer of energy from one point to another, or from one body to another, or from one part of the body to another, because of temperature difference. Now, the difference in temperature causes heat to flow. What does that mean? Let's say we have a solid material. Let's say this is a solid material. Inside this material, the material is made up of molecules. These are the molecules of the material. And a combination of atoms will give you molecules. So these are the molecules that are made up of this material. Let's say this is the material from copper. Now, if heat is being applied at this end, the molecules of this material will start vibrating. As they are vibrating, they will be transferring heat to the adjoining or next molecule, thereby transferring heat up to the end here. So heat is being transferred from area of higher temperature to the area of lower temperature. And the temperature, as we all know, is defined as the degree of hotness or coldness of a body. Now, heat energy is measured in joules. It's measured in joules. And then we talk of effect of heat on the body. Effect of heat on a body or material. One of the effects is this. We have rise in temperature of body. 2, we have change of state. Three, we have resistance. Change in resistance of the body. Change of resistance of the body. And 4, we have thermionic emission. Three, and so on and so forth. These are the effects of heat. So I will not be going into details. Whenever heat is applied to a body, the temperature of that particular body will change. The temperature will depend on the quantity of heat, or quantity or amount of heat given to the body. So if higher heat is supplied to the body, which means higher temperature will come up or will result. Then if lower heat is given, lower temperature will result. Now, change of state. Now, the application of heat causes change of state. Let's take, for instance, we have ice. Ice at, let's say, minus 7 degrees centigrade. Now, when you have ice at this temperature, the ice is in the state of the matter is in solid form. Now, the application of heat is given to that body. When heat is given to the ice, the temperature starts rising. As the temperature rises, it will change to ice at 0 degrees centigrade. Then from ice at 0 degrees centigrade, further application of heat will cause it to change to water at 0 degrees centigrade also. Then when you increase the temperature as well, it will change to water at 100. Then further application of heat will change to what? Steam at 100 degrees centigrade. So that is it. The resistance of the body varies with temperature, or is directly proportional to temperature. Now, resistance R is directly proportional to temperature T. Now, as you increase the temperature, You are trying to increase the resistance of a body. That is why we say increase in temperature increases the resistance of a body. For instance, when we talk of metals have higher resistance because of the way the molecules or the atoms are being arranged. And when you increase the temperature on a metal, the resistance of the body increases. So that's why we say metals have what we call positive temperature coefficient. That's what they call temperature coefficient. Temperature coefficient depends on the resistance of a body. As temperature increase, they have what we call positive temperature coefficient. While for matters or for elements, as temperature rises, they will fall. Has what we call negative temperature coefficient. Now let's talk about thermionic emission. Thermionic emission has to do with when light of sufficient frequency. If light of sufficient frequency falls on a matter, something happens to the matter. Electrons are being emitted. Now, the amount of electrons that are emitted will depend on the frequency of the incoming light or frequency of the incident light. Now, if the frequency of the incident light is high, then large amount of what? Electrons will be emitted. And for that to happen, that means that the electrons has to be given kinetic energy. They has to possess kinetic energy. Then they will now reach a point where we call the work function. Now, once they reach the point we call a work function, the electron will start emitting, and then they'll start moving, possessing a different kinetic energy, depending on the energy that is given to the electrons. So that is what thermionic emission is. Now, expansion of the body. Expansion of a body could be, a body could expand in three forms. It could expand in linear. That is what we call linear expansivity. It could expand in area. That is what we call beta or superficial expansivity. It could be expand in volume. That is what we call gamma or cubic expansivity. So the expansion of a body or expansion of a material here will depend on the quantity of heat that is being applied. Now let's go to measurement of heat itself. Now in measurement of heat, we will talk about the specific heat capacity. The specific heat capacity of the material. Now we have different materials. We have copper, we have water, we have kerosene, we have turpentine, we have naphthalene. These are different materials. Now, their specific heat capacity varies. Why is it that their specific heat capacity varies? It varies because of the way the molecules are being arranged. Now, what does specific heat capacity mean? The specific heat capacity of a material is the quantity of heat required to change a unit mass. A unit mass. A unit mass of a substance via 1 degree rise in temperature. We have a material, and then inside it are these molecules. These are the molecules. All of them gives you what we call the specific heat capacity. And the specific heat capacity, we say that quantity of heat is directly proportional to the mass and the change in temperature, that is delta theta. Now, delta theta tells you that this particular matter was existing at a particular temperature formerly before heat was applied. Now, let's say this matter was at, let's say, temperature of 5 degrees centigrade. Now, initially, or it was under what we call the ambient temperature, that is temperature of the outside or room temperature. Now you apply heat to this matter. Now the temperature now changes to, let's say, 15 degrees centigrade. Now there is a change in temperature. That change in temperature is as a result of heat. Heat has been applied, and the application of heat results to change in temperature. So the quantity of heat is directly proportional to the product of mass and change in temperature. Now we know mathematically that is equal to specific heat capacity. Given material, if for example we have copper, we have water, we have oil or palm oil. Let's say palm, let's specify it, palm oil. We have kerosene, and so on and so forth. These are different materials. The made up of the materials are being arranged in different forms. So their specific heat capacity will be different. So specific heat capacity from our relation will be equal to Q all over mass delta theta. Now quantity is in joule, all over mass in kilogram, and then theta is in Kelvin. So this is the unit of specific heat capacity. The specific heat capacity is measured in joules per kilogram per Kelvin. And now in measurement of specific heat capacity, we have two methods of measuring specific heat capacity. We have the calorimeter method or method of mixture. We have calorimeter method or method of mixture. Now, before I go into that, I will talk about heat capacity. Heat capacity. The heat capacity is the product of mass and specific heat capacity. So that means we have mass times specific heat capacity. That is it. Now, quantity of heat Q or H, either H or Q, is equal to heat capacity. So it could be given as heat capacity, which is MC times delta theta, mathematically. So that is it. Now, let's go back to measurement of specific heat capacity. Now, the specific heat capacity of a body could be measured by two methods, as I said earlier. We have the method of mixture and then the electrical method. Now, let's start with method of mixture. One, we have method of mixture. And two, we have electrical method. Now, in method of mixture, hot matter or hot materials are transferred to cold material inside a calorimeter. Now, let's say this is a calorimeter. Now, in this calorimeter, we have the calorimeter is used to measure the quantity of heat in this material. Now, we have this calorimeter, then we have a substance here. Let's say the substance here is water. And then we have what we call a stirrer. This is a stirrer. Now the idea of stirrer, and then we have this. This is a lagging. We lag the calorimeter. This is lagging. Now we have a stirrer inside the water. Now we have a lagging material. Now the idea of lagging is to ensure that heat lost by conduction is prevented. Lagging of calorimeter helps to reduce heat lost by conduction. So that is this. Then the function of the stirrer, which is this. The stirrer is equivalent to your soup spoon. We have a stirrer. Its function is to ensure uniformity, mixed. That is the function of the stirrer. The stirrer is equivalent to your soup. When you're cooking soup at home, you find out that you put your onion, you put your Maggi, you put your salt. For the whole thing to blend very well, you need a spoon. You turn it. When you are turning it, you are making sure that the components or the ingredients you put inside the water will move around the water. That is to ensure uniformity. That is the function of this stirrer here. What the stirrer does is to ensure that the incoming substance and the substance inside here are at the same temperature. Now, let's take, for instance, what happened is this. In the method of mixture, we have hot substance. Let's say we have, copper. This is a mass of copper at temperature. This is copper at temperature, let's say 150 degrees centigrade. And then this water inside the calorimeter was at, let's say, temperature of 40 degrees centigrade. Now you need to transfer this hot copper inside here. Now when you transfer the hot copper inside here, you find out that the temperature of the copper will drop, while as the temperature of the water will rise. The rising is because the water has gained heat from the copper, and then the copper has dropped its temperature. Now, to ensure the equal temperature of the system, you need a stirrer. Now, the stirrer will ensure uniformity of the whole system. Now, let's pick up one question and then you understand what I meant. A practical application of method of mixture. Number one, 150 grams of ice at 0 degrees centigrade is mixed with 300 grams of water, degrees centigrade. Then we are told to calculate the temperature of the mixture. Now, we are given this question to analyze. So we have an ice. We need to sectionalize, or we need to start analyzing the parameters into different components. We will say mass of ice. Mass of ice is 150 grams, which is the same thing as 150 divided by 1,000 to convert it to kilogram. And it will give us 0.15 kg. Now we have temperature. Temperature of ice. The ice was at this temperature, so we have 0 plus, we need to convert it to Kelvin, plus 273, which is equal to 273 K. The idea of converting it to Kelvin is because of the unit of specific capacity. Now, we have water. So we have mass of water was 300 grams, which is 300 over 1000, which is 0.3 kilogram. Now, temperature of butter was 50 degrees centigrade, which is 50 plus 273, which will give us 50 plus 273 will give us 323 K. Now, specific heat capacity. Specific heat capacity of butter is 4200 joule per kilogram per Kelvin, which is the same thing as specific heat capacity of the ice. Now, we will now start analyzing. We will now say final temperature of the mixture, or temperature of the mixture. Final temperature of the mixture is unknown. That is what we find out. Now, we say that heat lost. This guy is going to lose heat because it has a higher temperature, and this guy is going to gain heat. So, neglecting the environmental effect, neglecting the environmental effect, the heat lost by water at temperature of 50 degrees centigrade is equal to heat gained by ice at 0 degrees centigrade. So with that, we can now say neglecting the environmental effects, heat lost by ice or heat lost by water at 50 degrees centigrade is equal to heat gained by ice at 0 degrees centigrade. So that means this is for water, then this one will be for ice, mass times specific heat capacity times change in temperature. That is it. So now we will cancel specific heat capacity because they are the same. So we have mass into bracket theta initial was 323 minus theta final equal to mass of ice was 0.15 into theta final minus theta initial was 273. Now we will expand. By application of expansion, we have that 0.3 times 323 will give us 96.9 minus 0.3 theta final equal to 0.15 theta final minus 0.15 times 273, which will give us 40.95. Now we'll collect like terms together. So this guy will 0.15 plus 0.3 give us 0.45 theta final. So theta final will be 137.85 all over 0.45. Mathematically, if you shift the upper one to 2 decimal places, that means we have 3785 all over 45. So we have that our theta final will be equal to, we have 13785 divided by 45. It will give us 306.33 Kelvin. So this is the final temperature of the mixture between the two components. This gives you the final temperature of the mixture. Now, this illustrates a typical example of what we are talking about: heat gained by a substance and heat lost by a substance. Now, practically, environmental effects that could affect this calculation when you are performing experiments in the laboratory, but we neglected all of them and then compute and got our answer to be like this. So let us also pick up another question. Let us pick up another question and then we'll solve. This one says a metal compute or calculate the temperature change when 500 grams of heat is supplied to 500 joules, not grams. Joules of heat is supplied to 100 grams of basalt. Now, let us calculate the temperature change. It's a simple question. So, this is quantity of heat supplied to the water of this magnitude. The water of this magnitude got this quantity of heat. So we say quantity of heat is equal to mass times specific heat capacity times change in temperature. This represents change in temperature, or you can do it like this. If you're using first principle differentiation, you can say mass times C times delta theta. It means the same thing. So we are told to calculate delta theta. So quantity is equal to M times C times delta theta. So we are looking for delta theta will be equal to quantity over MC. Now our quantity of heat was this 500 joules. All over our mass was, we needed to convert the mass first. Our mass was 100 grams. 100 grams is the same thing as 0.1 kg because we will divide by 1,000 in order to convert it. So we have 0.1 multiplied by C, specific heat capacity of water, which is 4200 joule per kilogram per Kelvin. So we substitute it here, have 4200. So we have 500 over 0.1 times 4200, which will give us 420. So this we cancel this, we have 50 over 42. So we say 50 divided by 42, which will give us 1.19. That is the temperature change. The temperature change in the system. Temperature changes at the rate of this. And then we see how things goes. It says a metal of mass, a metal of mass 0.5 kg is heated to 100 degrees centigrade and then transferred to a well-lagged calorimeter and transferred to a well-lagged calorimeter. where like calorimeter. Of heat capacity, 80 joules per Kelvin, containing water of heat capacity of question. This is the heat capacity. This is the mass. This is heated to this. A heat capacity. Okay. Calculate the quantity of heat. Now, as we all know, quantity of heat, as I said, is equal to mass times specific heat capacity times temperature change. Or you can say that this is heat capacity multiplied by delta theta. Already our heat capacity has been given to us as this. So we need to now say that quantity of heat is equal to heat capacity multiplied by changing temperature. Temperature is this. We have 100 plus 273. So our heat capacity was 80 joule per Kelvin multiplied by 373, which will give us the quantity of heat. 80 times 373 to give us 2984. 2984 joules. So this is the quantity of heat that we supply to the water and then rise the temperature to this 100 degrees centigrade. So that is it. Now let's move over to electrical method. Let's move over to electrical method. We have dealt with method of mixture and then, well, electrical method of heat measurement. Electrical method. Now, in the electrical method, we have a coil, a system that supplies energy to whatsoever that is inside the calorimeter. And then the heat supplies work done by the electrical equipment is equal to heat gained by the calorimeter and its content. That is what is happening in the electrical method. We now have, let's say, this is a calorimeter. Now, inside the calorimeter, it's a lag. We have a stirrer. We have a liquid here. Then we have electrical system. Is a coil connected to, let's say, a source of energy. Now, the idea of this coil is to give energy to this system. So this is power source. So this is circuit. And then this is also circuit. The energy that is being supplied from this system will change the temperature of this. Now, electrical work or electrical power have electrical work all over time. So that is what power is. Or, am I correct? No. Electrical work is equal to power, electrical power. All over time. So we have that electrical power will be equal to electrical work multiplied by time. So power P is equal to work. Work is charge times what? Voltage. Multiplied by time. Or we can say that electrical power is equal to electrical work all over time. So we have that electrical power is equal to QV over T. But quantity of charge that flows through this coil, but Q is equal to IT. So power is equal to what? IT times V over T. This will cancel this. So we have I. So power is equal to I. Now, this is the power supply or the work done on this system to energize this system so that the temperature of the liquid or the content of the calorimeter will change. Now, let's pick up the question and see what we can do here. It says a block of aluminium. A block of aluminium is heated electrically by a 30-watt heater. If the temperature rises by the temperature rises by 100 degrees centigrade in 5 minutes. In 5 minutes, the heat capacity of the aluminum is the heat capacity of the aluminum is now the electrical power or work done by this heater, electrical heater of this amount is equal to power times time. So work done, electrical work done by the heater is equal to electrical power times time. Now, I've been hearing about electrical power. What is electrical power? Power is the rate of doing work. When work is done, resistance is what we call power. So we have that electrical work or work done is equal to power times time. Therefore, work done on the aluminium block is equal to mass of aluminium times specific heat capacity of aluminium multiplied by change in temperature of aluminium. But mass times specific heat capacity of aluminium will give you what we call heat capacity. Heat capacity of aluminium temperature. So Cp will be Pt all over delta T. So at this particular point, our power was 30 watts multiplied by our time was given 5 minutes, which is 5 times 60 all over. Change in temperature is 100, which is 100 plus 273. So this will give us 30 times 300 all over 373. And then we generate a function. We have 30 times 300, which is 9,000. 9,000 divided by 373 divided by, and this is temperature, joules per, this is work, and this is temperature, joule per Kelvin. So that is a typical example of what we are doing. Now let's solve other questions too, and then we move over. The question says, a heater marked oven, a heater marked 60 watts evaporates 6 times 10 to the power minus 3 kilogram of boiling water in 66 seconds. What is the specific latent heat of vaporization? What is the specific latent heat of vaporization. Now, when we talk about latent heat, we are talking about hidden heat. The word latent means hidden. Latent means hidden. Something that is unseen, something that is uncovered, something that is being shielded or protected or screened. Now, this is the heat that causes a change in temperature. It causes change of state without changing temperature. It is a heat that causes change of state without changing temperature. But let's first of all analyze this calculation. I will come over to that. Electrical work is equal to work done on this boiling water is equal to mass of water multiplied by latent heat of vaporization. Latent heat of vaporization, the heat that causes the water to escape from the kettle or from the pot when you are boiling the water without changing temperature is latent heat of vaporization. So it is ET power times time equal to mass times latent heat of vaporization. And from our parameters, we have that power was given to us as 60 multiplied by our time was 60 watts also equal to mass, which is 6 times 10 to the power minus 10 multiplied by L, which is latent heat of vaporization. So this will give us 3600 60 to 3 all over 6 times 10 to the power minus 10. This one will go up. We'll now have 3.6 times 10 to the power 3 plus 3 all over 6. So L will be 3.6 times 10 to the power 6 all over 6. So we can now divide it. You can say 3.6 divided by 6 will give us 0.6. So it will give us 0.6 times 10 to the power 6. We can express this as standard form. We have 6 times 10 to the power minus 1 plus 6, which is 6 times 10 to the power 5. Now it's joules per. This one is joule per kilogram. That is it. Joule per kilogram. That is how it is. Now let us move over to latent heat. Talk about latent heat. So let's talk about latent heat. The word latent means hidden, as I said earlier. Now, latent heat is the heat that causes a change of state without change in temperature. Now, why is it that such a thing is happening? The thing is happening because work done on the system is used to break the bonds that is holding the molecules of the matter together instead of rising the temperature of that particular matter. That is why we have latent heat. Now let's take, for instance, we have water, which is H2O. Now water has two elements, consists of hydrogen and oxygen. So in each molecule of water, you're going to have an element of hydrogen and what? Oxygen. These are the molecules of water, even though that they are not really cohesive like this, even though they are not really bonded together like this. But what happens is this, that when you heat water, you find out that the molecules that held you find out that the forces or the bonds that held the molecules of water together need to be broken. And once these bonds are broken, the water will change from one state to another. Now, in the case of latent heat, because of its nature, or because of why we call it latent heat, instead of this heat you supply to this system to break the bonds and then rise the temperature of this water or the temperature of the matter, what it does is this: it only breaks the bonds and leave the temperature constant. The temperature remains the same. So that is why we call it latent heat. Now, let's say a graphical situation is this: minus 15 degrees centigrade. We have ice inside a calorimeter at minus 15 degrees centigrade. Now, we needed to heat this ice so that it will change from one state to another. Rather, the ice will move and change to ice at 0 degrees centigrade. Now, further application of heat to the system will change the ice to water at 0 degrees centigrade. And then, when heated also further, it will change to water at 100 degrees centigrade. And then when heated further, it will change to steam at 100 degrees centigrade. That is what is happening here. Now, from ice at minus 15 degrees C to ice at 0 degrees C, there is a change in temperature. Why? Because work done by the system here is doing two things. The heat applied to this calorimeter is performing two things simultaneously. It breaks the bond, it changes the temperature. That is what is happening here. So there is what we call mc delta theta. Now, here is the mass of the ice. C represents the specific ice at 0 degrees centigrade to water at 0 degrees centigrade. There is no change in temperature. Why? Because the heat supplied at this particular point does only one thing. What the heat does is this: it changes the state from ice at 0 degrees C to water at 0 degrees C without a change in temperature. So we have mass times latent heat of fission. Now, from here we have water at 0 degrees C to water at, there is also a change in temperature. So we have mass times specific heat capacity of water times change in temperature. That is what is happening here. But finally, as water reaches 100 degrees centigrade, the bonds to also broken, or the bonds of water to broken without change in temperature. So we have mass times latent heat of vaporization. That is what is happening here. So in this case, we can be told to calculate the quantity of heat supplied to a network like this. And then in that case, we know that there is the quantity of heat here will be, let's call here Q1. Q1 will be mass times latent heat of fusion of ice times change in temperature. For Q2, we will have mass times latent heat of fission, ml. Then for Q3, we will have mass times latent heat of water. So we have mc delta theta. And then for Q4, we'll have mass times latent heat of vaporization. Now, so the total quantity of the system will be Qt is equal to Q1 plus Q2 plus Q3 plus Q4. Alternatively, Qt could be written as M L delta theta plus ML plus MC delta theta plus ML. That is how the system looks like. So let's pick a typical example and then do justice to it. See what the system is talking about. We have the quantity of heat energy required to melt completely. The quantity of heat energy (1 kg of ice at latent heat of fusion. Latent heat of fusion as 3.5 times 10 to the power 5 joule per Kelvin, joule per kilogram, sorry. And then we have specific heat capacity of ice, 2.1 times 10 to the power 3 joule per kilogram per Kelvin. That's what we are told to calculate. So we will draw the network diagram. We have an ice at this temperature. What quantity of heat will melt it completely? Melt it completely, so it has to change to water. So that means we have ice inside a calorimeter to ice at 0 degrees centigrade. And from ice at 0 degrees centigrade, it will change to vata at 0 degrees centigrade. As we said, there is a change of state here. So we have MC or ML delta theta. So there is no change of state, ML. So let's calculate here. Let's call here Q1. And then let's call here Q2. So Q1 minus theta initial. So this will give us 1 times latent heat of fusion is 3.5 times 10 to the power 5 into our final temperature will be 30, will be 0 minus bracket initial will be minus 30. So we have 1 times 3.5 times 10 to the power 5 into 0 plus 30. Because minus times minus will change to plus. So we have 1 times 3.5 times 10 to the power 5 multiplied by 30. So this will give us 1 times 30 times 3.5 plus 0.5 to give us 1, 2, 3, 4, 5, 6, 7, 8. So 1.05 times 10 to the power 7 joules. That is the quantity of heat here. Because yes, that's the quantity of heat here. Now let's calculate. So our mass, there's no change in temperature. Our mass was what? 1 times latent heat of this is 2.1 times 10 to the power 10, which is 2.1 times 10 to the power 10 joules. Now, total heat that could make the system QT will be Q1 plus Q2. And this will give us this 1.05 times 10 to the power 7 joules plus 2.2100, which is 105 or 10502 100. So we have this as 1.0502100 times 10 to the power 4, 5, 6, 7 joules. That is the quantity of heat that melts completely the ice to water. That's number 1 question. Now let's continue again. So let's do one more calculation and then we'll move over to upthrust in liquids. The question says, calculate the specific heat capacity of a material for which heat of 2.52 times 10 to the power 4 joules supply 0.3 kg temperature 20 Kelvin. This is a good marker. So we're told to calculate so we know that quantity of heat, the heat supplied to this material, we don't know the material, is equal to the mass of the material times the specific heat capacity of the material times the change in temperature. So in this case, the quantity of heat, mass of the material was 0.3 multiplied by change in temperature 20 multiplied by specific heat capacity. That's what we are looking for. So now say specific heat capacity will be 2.52 times 10 to the power 4 all over 0.10 times 20, which is 2.52 times 10 to the power 4 all over 0.3 times. We now do 2.52 exponent 4 divided by 6 to give us 4200 joules per kilogram per Kelvin, which is specific heat capacity of water. Water has specific heat capacity of, so the specific heat. So let's move over to, we're going to move over now to forces in fluid. Now let us talk about equilibrium of bodies in liquids. let's talk about equilibrium of bodies in liquids. Now, let's assume that you went inside a stream this morning, and then you fetch water. When you fetch water and then you were coming out from the stream, you find out that as you're walking outside, as you're walking towards the seashore, the weight of the bucket which you carry appears to be reducing as you're coming out of the sea. While you are in the sea, the weight was very, very insignificant. But as you're coming out of the sea, the weight starts increasing until you come out of the sea. You now had the real weight of the bucket. Or you are drawing something from a well or from a tank, a local tank, you find out that as the bucket sinks inside, as the bucket submerges inside the water, as you're pulling the water out as you're pulling the bucket out from the water appears to be light. I want to illustrate it. We have, let's say this is a well, and then you have a bucket. The bucket is up to this point. The bucket will be weightless. It will appear as if it doesn't have weight until it comes to this point. So there is liquid or fluid. It could be a fluid, could be gas, could be water. Now, as this is coming out, there is what we call an upthrust. An upthrust, a force on the liquid is pushing this up, and we call it upthrust. Well, until it appears to the boundary between the water and the air. Now you start feeling the effect of the weight of the water. Now, if the weight of the water meant, if the weight of the bucket meant it is in water is W2, and the weight of the water meant it is in air is W1. Therefore, upthrust U will be equal to W1 minus W2. So, which is the same thing as saying that this is weight. Because of this effect, we experience upthrust. Therefore, upthrust is equal to W1 minus W2. So W1 will be equal to W2 plus upthrust. Therefore, W1, that is weight in air, is greater, which says that if a body is partially or wholly immersed in water, we have what we call Archimedes. Archimedes principle. Archimedes was a Greek scientist or a Greek philosopher. So he was in his bedroom, taking a shower inside his bed or inside his bathtub. He filled the bathtub with water, and then he went inside. Splash on the basement is equal to his weight. He came out and shouted, "Eureka!" That was what he said. So he found out that the weight of the water which splashed on the basement of his bedroom was equal to his weight. So that was what he said. And then he says that if a body is partially or wholly immersed, this body is wholly immersed inside a fluid. But when you have a container that stays like this is vessel level, and then part of the container is here and part is outside. Now this is the container. So inside liquid. Now, if the body is partially or wholly immersed in a fluid, it will experience a force or an upthrust which is equal to the weight of the liquid displaced. That was what he said. Now, if the body is totally immersed in a fluid like in case 1, this is case 1. If body is totally immersed in a fluid, which could be water or gas, the upthrust of the object multiplied by volume of the liquid times g, or acceleration due to gravity. Acceleration due to gravity. So that is how it is. So if a body is totally immersed in a fluid, it will give us upwards with the volume of the liquid, volume of the object, density of the liquid, and then time acceleration due to gravity. Now, in case 2, whereby the object is 1/3 submerged. So this is case 2, when 1/3 of the object is submerged inside the fluid. So we have that the upthrust in this case, upthrust or force exerted by the fluid on this particular object will be 1/3 times volume of object times density of liquid times g. So we can also say that this is upthrust equal to V/3 times density of liquid multiplied by g. That is how it is in the case when the body is submerged inside the fluid. Now, let us talk about experiment to determine the verification of Archimedes' principle. Experiment to determine the verification of Archimedes' principle. weighing balance, or we have a weighing balance, a graduated weighing balance with a hook. Is a weighing balance graduated with a hook. And then you have a cock. This is a cock. And then you have a hook attached to it. When this cock is being placed on this spring balance, we have a weight W1, which is weight in air. Now, let's imagine this stuff inside a beaker with opening, a Eureka tube, sorry, a Eureka can. This is a Eureka can. And then this is a beaker. This is a Eureka can. And then when we immerse this stuff inside this fluid, when we immerse this stuff, some quantity of water fell down. Some quantity of water fell on the beaker. Now let's represent the weight here as W2, so that we'll have that weight of cock in air. W2 is equal to weight of W2 is weight of object in water. W3 is equal to weight of empty can. Weight of empty can. And is weight of beaker plus weight of displaced water. Weight of beaker plus weight of displaced vessel, which is this one here. So we'll now have that from our experiment. We'll have that apparent loss of weight of object, apparent loss of weight when it is in air, and then when it is in a liquid. And then we'll now talk about minus W3. That gives you that. Now, experiment has proved that because of the effect of upthrust, that the apparent loss of weight in air, apparent loss of weight of object is equal to weight of the liquid displaced, or weight of the fluid displaced. So let us pick one or two calculations. The apparent weight loss in weight of the apparent weight toss, the apparent loss in weight of objects, which is upthrust, is thrust. That is upthrust is equal to weight. Or we go into flotation. Flotation. let's pick a question. A piece of cork floats in a liquid. What fraction of its volume will be the mass? Okay. Let's start. A balloon whose volume is 300 meter cube is filled with hydrogen. Whose volume is this? Is filled with hydrogen. If the density of air the density of air is 1.3 kilogram per meter cube, find the upthrust on the balloon. So we have G is equal to 10 meters per second. So let's start. So we have that the upthrust on the balloon, upthrust, volume of the balloon multiplied by the density, kilogram per meter cube, multiplied by 10 meters per second square. So this guy and this guy will go. So we have 3,000 times 1.3. So we have kilogram meter per second square. So this will give us the upthrust. The upthrust on the balloon. We have 300 times 10 times 1.3. And this will give us 3,900. So it will give us 3,900 kilogram meter per second square, or 3,900 Newton. So that is the upthrust in that particular question. So let's go further. The next question says, an object of 1 meter cube, an object of volume 1 meter cube, and mass 2 kg is totally immersed in a liquid of density 1 kg per meter cube. We calculate the upthrust. Calculate the apparent weight. Apparent weight. So from here, we have that upthrust is equal to weight in air minus weight in water or liquid. So what do? We need to calculate the upthrust because the body was fully immersed. So upthrust will be W1 minus W2. This is the apparent weight. That is what we are looking for. They say you should calculate the apparent weight. So upthrust, since it is fully immersed, will be equal to volume of liquid times density of liquid multiplied by G. So volume of liquid is 1 times density of liquid is 1 times. Let us find the weight in air. Weight in air, which is W1, is equal to mg. This is the mass. So W1 will be 2 times 10, which is 20 Newton. Therefore, upthrust is equal to W1 minus W2. So we now take this man to this side. W2, which is the same thing as apparent loss, apparent weight, will be equal to W1 minus upthrust, which is the force on the liquid. So W1 is 20 Newton minus the upthrust, which is volume times volume of the liquid times density of the liquid, volume of the liquid times density of the liquid times G, which is 10 Newton. So our apparent weight will be 10 Newton. Answer. let's continue. We have another question. All these questions are jam questions, so be attentive while I'm resolving them. We have another question that says, an object weighs this in water. An object in R. What is the upthrust exerted on the liquid? What is the upthrust exerted on the liquid? And that liquid is water. So that's another jam question. Now, first of all, we need to, as we all know, we know that upthrust in liquid, which our case is Vasa. So that means that upthrust U will be W1 minus W2. So how do we calculate W1, which is weight in air? W1 is weight in R and is equal to what? Mg. So our mass in air will be equal to 30 times 10, which is 300 Newton. Then let's find weight in water. W2 is weight in Vasa, which is also Mg, and is the same thing as 22 times 10, which is 220 Newton. Now let's calculate the upthrust of the liquid on the object. So our W1 is 300 minus 220, all in Newton. So this will give us 80 Newton. That is the upthrust, the force the liquid exerts on the bucket. That is that force there. That is that force. Now, we will continue to resolve questions. We'll do justice to questions. Do justice to questions. Oil, the density of this, we have volume, the density of 400 cm cube of oil was 0.9 kilogram per meter cube before frying. If the density of the oil was this after frying, assuming no loss of oil to spillage, assuming no loss of oil to spillage, comma, its new volume was this. So now let's get the mass of the oil. Mass of the oil before frying. Mass of the oil before frying will be, since we have density as mass over volume, so mass will be density of oil multiplied by volume of oil. So this will give us what? So the mass will be the same since there is no oil spillage. So density here will be 0.9 kg per meter cube multiplied by 400 meter cube. So meter cube cancel meter cube. We have 0.9 kg times 400 to give us the mass of the oil. So we have 60 kg. That was the volume of the oil, the mass of the oil. Now, if the density of the oil was this after frying, assuming no loss of oil to spillage, new volume will be. Now let's calculate the volume of oil when it has been fried. Volume of oil after frying will be mass of oil all over density of oil after frying. So our mass was 360 kg, all over our density was 0.6 kg per meter cube. So which is 3600 over 6. So we have kg divided by kg over m cube. 100 into kg times m cube over kg. So this we cancel this. We have 600 meter cube. So change this new volume. This new volume is this. That is the new volume, 600 meter cube. Because the oil has spread before it was clogged together. Just like when you have palm oil or fat. Fat will clog together, but when you cook it on a fire, it will expand. So that is a typical example of what is happening here. Now, let's do justice to another question. Okay. Let's solve one more question. It says a piece of cork floats in a liquid. What fraction of its volume will be immersed in the liquid? We have density of cork. Density of cork. 0.25 times 10 to the power 2 kilogram. The density of so that is what is happening here. Let the total volume of cork be V1. Mass of cork will be density times volume. Mass of cork will be density times the volume when the cork floats. Each weight equal to the weight of the liquid displaced. Each weight equal to the weight of the liquid displaced. So mass of cork multiplied by volume, which is V1. So density of cork was 0.25 times 10 to the power 2 kg per meter Q times V1. Then we say that when the cork floats, its weight equal to the weight of the liquid displaced. When the cork floats, its weight is equal to the weight of the liquid displaced. So when the cork floats, its weight 0.25 times 10 to the power of 2 kg per meter cube equal to weight of the liquid displaced will be, this is like the volume of the submerged. This. So what do we have? We have V1. We have 0.25 times 10 to the power of 2 V1 equal to 1.25 times 10 to the power of 2 V2. So what do? We take the ratio. We say 0.25 times 10 to the power of 2 divided by 1.25 times 10 to the power of 2 equal to V2 over V1. So that is the ratio. The ratio we are told to take. So this guy and this guy will go. We shift to 2 decimal places here. We'll have 25 over 125 equal to V2 all over V1. So 5 here is 1, into here is 5. So the ratio will be 1 over 5 equal to V2 over V1. So that's the final answer. So that is, it says, what is the fraction of its volume will be in mass? So this is the fraction of the volume that will be in mass will be equal to 1. We have another question. So we have another question that goes like this. It says, at what depth okay. It says, at what depth below the sea level would one experience a change in pressure equals 1 atmosphere. Density at sea level is this. 1 atmosphere is this. Density at sea level 1013 kg per meter cube. 1 atmosphere. 0.01 times 10 to the power 5 Newton per meter square G. Meters per second square. So we're talking about the depth. Pressure here is rho gx. So we are told to calculate the height. So how do we get the pressure? Pressure is this. Pressure has been given as this. So 1 atmosphere is this, and is equal to 10 to the power 5 Pascal. So which is 0.01 times 10 to the power 5 is equal to rho, which is our density, 1013 times 10 multiplied by h. So h will be 0.01 times 10 to the power 5 all over 10137, which will give us 0.01 exponent 5, which is 1000 all over 1013 times 10, which is 10130. So 1000 divided by our answer will be 0.0. Pressure equals 1 atmosphere. So at this height, one will experience a pressure that is equal to 1 atmosphere.